Think back to the last time you ate some jelly beans. Were you selective about which colors you ate? Whenever I'm eating jelly beans, I go for the green ones first. Just like the mixture of jelly beans, most substances are mixtures of things. Remember that there are two types of matter that exist: pure substances and mixtures. A mixture is a physical combination of two or more substances that are mixed but not chemically combined. The components of a mixture maintain their own physical properties. An example of a mixture is salt water. If you were to drink salt water, it would taste like water with salt in it. Mixtures come in two main types: homogeneous and heterogeneous mixtures. A homogeneous mixture is a mixture that is uniform throughout, meaning that one part of it has the same distribution of ingredients as another part. A heterogeneous mixture is a mixture that is not uniform throughout, meaning that there is an unequal distribution of the ingredients of the mixture. Air is a homogeneous mixture of many different gases, including oxygen, nitrogen, carbon dioxide, and water vapor. I know it is homogeneous because each breath I take will contain nearly the same ratio of ingredients. Homogeneous mixtures are sometimes called solutions, especially when it is a mixture of a solid dissolved in a liquid. An example of a heterogeneous mixture is a chocolate chip cookie. It contains sugar, chocolate chips, butter, eggs, and flour. Each bite I take is likely to contain a different amount of chocolate. Heterogeneous mixtures are easily distinguished because their different components can be seen as individual substances, whereas a homogeneous mixture all looks the same. The rest of this lesson is going to go into detail on a few of the many ways a mixture can be separated into more individual ingredients. The first and most obvious way to separate a mixture is to manually separate it. This is probably what you did when you had a bag of jelly beans and picked out which color you wanted to eat. My next example involves a mixture of salt, sand, and iron filings. All of the particles in this mixture would be about the same size. So how would you separate them? Would you take a tweezers and separate them all out? This may get a little time-consuming, so one thing you may want to do is use a magnet. This uses magnetism to separate out the iron. So now the iron is out. How would you separate the salt and sand? To figure this one out, we need to look at some of the physical properties of salt and sand. You may have noticed that salt has the ability to dissolve in water, where sand does not. So I would add some water to this mixture and try to dissolve all the salt, leaving the sand to sink at the bottom. Our next technique is filtration, and it's one of the most common methods for separating a mixture in a chemistry classroom. When you brew coffee, you may rely on a coffee filter to keep the grounds from getting in your drink. If our salty water and sand mixture is poured through a filter, the salty water would go through, leaving the sand behind. This is because the molecules of salt are broken up enough and the molecules of water are small enough to go through the filter, leaving the large crystals of insoluble sand behind. Last on our list is separating the salt from the water. There are two ways we can do this. The first is evaporation. It may take some time, but eventually the water will evaporate, leaving the salt behind. This is sometimes called crystallization, because the solid salt will form crystals as the water evaporates. If you're short on time, you may want to take advantage of the boiling point of water, which is much lower than the boiling point of salt. By heating the water to its boiling point, you're allowing it to change from a liquid to a gas, eventually leaving all of the salt behind. This process is known as distillation, and it's used in the purification of all kinds of things, from water to crude oil. For our last example, we're going to go back to the jelly beans. Did you know that most dyes to make candy are actually mixtures of different pigments? The same is true for dyes that are used in markers and ink pens. Is it possible to separate the pigments of jelly beans or markers? You may know the answer to this if you've ever spilled water on a document and watched the ink bleed into different colors. What you are seeing is a separation of the pigments of ink because each pigment has a different attraction to the water based on subtle differences in each pigment's polarity. Chemists use these small differences to separate some mixtures using chromatography, which means color writing. In paper chromatography, a small dot of the ink or dye to be separated is placed near the bottom on a piece of superabsorbent paper. Let's look at my green jelly beans. If I were to dissolve a little of the outer green layer of the jelly bean in water and put a little dot of that green dye on a piece of chromatography paper, it may look something like the middle dot in this picture. The paper is then put in a container with a small amount of solvent, maybe vinegar or ethanol. Can you picture what happens to one end of a piece of paper when it's touched to some water? The paper draws up the water in a process called capillary action. As the paper is absorbing the water, some of the water mixes with the dot of dye that informs a solution with the water traveling up the paper. This green has now separated into two different colors, yellow and blue. The attraction that the dye has with the paper will determine how far the dye travels up the paper. Dyes that are more attracted to the paper won't travel up as high, and dyes that are not as attracted to the paper will travel up the highest. Once the solvent reaches the top of the paper, the line where it finishes is marked, and the chromatograph is removed and allowed to dry. The distance that each dye travels is measured from the starting point, and a value called a retention factor is calculated. The retention factor, or RF, is the distance the dye travels compared to the total distance the solvent traveled. So in this example, we would calculate the RF for the blue dye by taking the distance between points 1 and 2 divided by the distance between points 1 and 4. Notice that you will never have a retention factor that is more than 1 because the dye cannot travel farther than the solvent carrying it. Also, the RF does not have any units, because if you take a unit divided by the same unit, they both cancel out. Chromatography can be related to a school bus at the end of the day. After school is let out, all of the students get on the school bus. Then, as the bus drives around, kids are let off when the bus stops at their stop. Of all the separation techniques you may be asked about, chromatography is the most complicated, and in paper chromatography, it relies on the differences in attractions between the mixture components and the paper or solvent you use. Distillation is a way to separate mixtures based upon differences in boiling point, usually to separate two different liquids that formed a solution. Evaporation and crystallization are separations based on the ability of one substance to evaporate easily, usually water, and another substance that does not readily evaporate, usually a salt. The simplest of the separation techniques include using a magnet, manually separating, and filtering.